All right, good morning, everyone. Welcome back. So I did send out an announcement saying that the relations notes and the notes for chapter 17, which is relations, and chapter 18, which is on cosets, are available. And these are two, in some sense, they're relatively quick sections. They're just laying some of the groundwork material that we're going to need for our final topic, which is the Rubik's Cube. So I hope to get to the Rubik's Cube. Maybe we'll get to it on Friday. Definitely by next Monday, though, we'll get to it. And the challenging part, so if we think about where we come from the swap puzzle, the 15 puzzle, and then the oval track puzzle. All of them, in some sense, have the feature that once a tile is in its proper location, it's home. Right? The disk 1 is in box 1, great, it's in its home box. There's no orientation attached to the tiles. Whereas with the Rubik's Cube, you could have a corner piece, a corner cubie, that's sitting in its proper, let's say, position or location, but it's just been rotated, or an edge that's in its proper location, but it was flipped. And so for our pieces on the Rubik's Cube, we've got two different aspects to them. One is the position that the piece is supposed to be in, and the other one is, once it's in that position, what is its orientation? And it's that orientation issue that makes the Rubik's Cube slightly more challenging than the other puzzles. And this also indicates that we're going to need a little bit more theory in order to unpack these questions about orientation of pieces in comparison to their position. And that's really where chapter 17 and 18 come in. They give us a little bit more theory that will help us understand some of the more subtle aspects of the Rubik's Cube. So the first section, chapter 17, is on relations. So this is a concept from set theory. What a relation is just, if you have a set, it's a way to talk about how elements are related to each other. We're going to be more interested in equivalence relations, and this is a way of partitioning a set. So that means the first thing I'm going to introduce here is just the idea of a set partition. So what is a partition of a set? Well, if I have a set a finite collection of subsets, so I've called them here A1 through AN, with the properties that the union of all of those subsets is all of A, and they are pairwise disjoint. So they have nothing, no two elements of this partition have anything in common. So this is what we call a partition. It's just a breaking down of our set A into a finite collection of disjoint subsets. So where does this come into play? Well, immediately on the Rubik's Cube, if we look at a partition of the cubies, so all of the movable pieces on the cube, the corner cubies, the edge cubies, even the center cubies. This collection of all the cubies can be partitioned into three disjoint sets. There's E, which I use to denote the edge cubies. There's V, which denote the corner cubies or the vertex cubies. And I didn't use C there because I want to use C for the center cubies. So all of the movable pieces on the Rubik's Cube, which we call P, they can be split up into three disjoint sets: edges, corners, and centers. Another partition that we've exploited all throughout this course is this idea that a set of integers can be split up or partitioned into two sets: the even integers and the odd integers. And we've made exclusive use of that through this idea of parity of a permutation. So those are two different partitions that are going to be quite important for us. And now let's see how we can actually create partitions in other ways. And so this is this notion of using a relation to do it. Yeah, exactly. So like in a Venn diagram, none of the circles are going to touch exactly. And I'm just looking at the next comment. Yeah, exactly. And no elements are outside of the circles. The circles contain all of the elements. So that's exactly what a partition is. Splitting up of your set into a bunch of disjoint subsets that contain all of the elements that we're interested in. Okay, so a relation. A relation. So if we got, so all of this starts with a set. So we've got a set A. We're going to try to get to the fact that we can create partitions in a different way. But above, we talked about a partition of A. Now we're going to talk about something else, not a partition anymore, but this idea of a relation on a set. What is a relation on a set? A relation is just a subset of ordered pairs. So it's a subset of A cross A. So a relation is just a collection of ordered pairs of elements from A. That's it. That's all a relation is. I've called it here this fancy R for relation, but it's just a subset. So it could be empty. It could be the empty subset. That would be the empty relation. It could consist of the entire Cartesian product, A cross A. Under that condition, we'd just say every element is related to every other element. Or it could be something in between. And that's going to be the more interesting cases for us. If the ordered pair xy is in the relation, we just say x is related to y. And we sometimes write x, r, y for simplicity. The key thing to note here is we say x is related to y. We don't say y is related to x, because relations, just in and of themselves here, if x, y is in the relation, that doesn't tell us anything about whether y, x is in the relation. So a relation is a set of ordered pairs, but the ordered pairs don't have to be symmetric in this way. If 1, 2 is an ordered pair in the relation, that doesn't mean 2, 1 is. So this is one directional, and that's why we say x is related to y. We're not going to say y is related to x unless y comma x is in the relation also. Then we would say y is related to x. But here, x is related to y. And we sometimes write x, r, y for short. So what's an example? Well, for example, if we let C be the collection of all configurations of Rubik's Cube, so all possible ways you can scramble it up, twisting faces, get all the possible configurations, of which we know how many there are, 4.3 times 10 to the 19. There's a lot of them. We can define a relation on that set. The relation we will define is that x is related to y, so configuration x is related to configuration y, if we can transition from x to y by doing a quarter turn. So for example, here's a configuration, and then I do a quarter turn of one of the faces. That's another configuration, and it is related to the original one. So the original one, the solved one, is related to this one because I went from the solved one to this one, and that's what it takes to be related. But we also have symmetry in this case. Starting with this configuration, I can do a quarter twist, and I get back to the solved one. So in this case, x is related to y, but also y is related to x. Now I could do it again. I could say, there's a configuration that's related to the solved state. But then from this one, I could do a quarter turn of another face. Maybe I'll call this configuration Z. So the solved one was related to that. So solved one, let's call it configuration X. It was related to that one I just had. Which one was it? This one here. This is configuration Y. This configuration is related to this one, which I'll call Z. But this configuration is not related back to my original X, because I can't take this one and go back to the solved state by doing only one quarter turn of a face. So here I have X related to Y, Y is related to Z, but X isn't related to Z because I can't go from the solved state to this one with one quarter twist. Okay, so that's the idea with being related, is you've got a set of objects and you're just going to define as to how one gets related to the other. Now, there's some deficiencies in that one I just introduced. For example, if X was related to Y and Y was related to Z, so solved state, quarter turn, solved state, quarter turn, that one's related to the solved one. Do another quarter turn, that was related to the one I just transitioned through, but this isn't related to the solved one. Kind of deficient in a sense. I kind of want my relations to be what we call transitive, that if X is related to Y, y is related to z, then x and z should be related to each other. There's a couple of other things we want our relations to satisfy, which will make them quite useful for us. And that is, I want an element to be related to itself. And I also want that if an element is related, so if A is related to B, then I also want B to be related to A. So I want symmetry involved. If I have those three conditions, we call that an equivalence relation. So for us, our focus is going to be on equivalence relations. So that is subsets of A consisting of ordered pairs with these three properties. That A is in the relation. So A is related to itself. And that's true for all elements of A. I also want it to be symmetric, that if A is related to B, then B is related to A. And I also want it to be transitive, that if A is related to B and B is related to C, then that means A is related to C. And if we have all of these three properties being satisfied for our relation, we call it an equivalence relation. And it turns out that equivalence relations are the key to partitioning sets. So any partition I have of a set gives rise to an equivalence relation. And if I have any equivalence relation on a set, that gives a way to partition it. So this is our goal, is to use equivalence relations to partition things. So let's just get a feel for what equivalence relations are. Maybe one bit of notation first. So when we're talking about equivalence relations, instead of using the X, R, Y notation, we often use this tilde notation. So I often write this instead of X, R, Y. And we read that as X is equivalent to Y. And sometimes this tilde is just replaced with a triple equal sign. So X and then triple equal sign Y to mean that X is equivalent to Y. So we'll either use tilde or triple equal sign when we're talking about an equivalence relation. So here's some examples. So let P be the set that we're interested in, and it's the set of all people alive today. So all the people, current living people on the world right at this moment. We're going to consider some different relations on this set. So the first one, X is related to Y if X is a sister of Y. So X is related to Y if X is a sister of Y. And let's just figure out, is this relation reflexive, symmetric, transitive? If it's all of those three, then it's an equivalence relation. So let's figure out if these ones are. So X is a sister of Y. Is this reflexive? Is this reflexive? So you can scroll back up and see, what does reflexive mean? Reflexive means that an element is related to itself. So can a person be their own sister? And in fact, to be reflexive, it means that has to be true for all people. Yeah, no, it's not reflexive. So a person is not their own sister. Is it symmetric? If X is a sister of Y, is it necessarily the case that Y is a sister of X? Yeah, exactly. So X could be a sister of Y, which case X could be female and Y could be male, but Y would then be the brother of X in that case. So this is not symmetric. So symmetric means that it's always going to be the case that if X is related to Y, then Y is related to X. In this case, we can think of an example where that's not true. In fact, I just think of my own children. I have one boy, one girl. So one is the sister of the other, but it's not symmetric. The other one is not the sister of the other one. How about transitive? If X is a sister of Y and Y is a sister of Z, is it necessarily true that X is a sister of Z? So if X is the sister of Y and Y is the sister of Z, then is X the sister of Z? So maybe we're thinking of, we got a family tree here. We got a mom and a dad, and they give rise to, in this case, we got 3 children. We've got child X, child Y, and child Z. And if X is a sister of Y, so that means if X is a sister of Y, that means X is female, or at least that's how we're using the term sister in this context. So X is female and is a sibling of Y, and Y is a sister of Z. So from that, we're just getting that Y and Z are siblings of each other. And so then X and Z should be siblings of each other. And because X is female, then X is a sister. It's a sibling and a female sibling of Z, so it should be a sister. So it looks like, yeah, we're getting that it's transitive in this case. Is it an equivalence relation? No, because to be an equivalence relation, we have to have check marks all the way across. Maybe I'll switch that pink check mark to a green check mark, just to distinguish in terms of colors, because what we'd like is we'd like 3 green check marks across the board in order to determine that it's an equivalence relation. Okay, so let's look at the next relation. This relation R2. X is a sibling of Y. So is it reflexive? Is X a sibling of themselves? Is it for every person in the world, are they their own sibling? What do you think? Yeah, we got a bunch of no's. It turns out to be a curious thing to do with language. Exactly, that is a confusing question. It actually has to do with language and culture. So apparently I was reading online, so a single person's perspective on this. This person happens to be of Malaysian descent, and the claim is that in Malaysia, they do refer to themselves as their own sibling. So if someone says to you, how many siblings do you have? And you're an only child, you would say, I have 1 sibling. It's myself. So it turns out that it is a hard question because it's cultural. In North American society, we seem to have the way of speaking about siblings in that if you're an only child and they say, do you have any siblings? You'd say no. Or if you had a single sibling, so there I go again, right? I'm sort of imposing on this. If you are a child in a family that consists of 2 children, in North America, you would say you have 1 sibling. So I'm going to put an X here because in North America, in the way we generally talk about siblings, we say no in this case. Do you have a sibling if you're an only child? But this is not. I'm not being definitive here. I'm saying it all depends on your cultural background. You could have a check mark here. You could refer to yourself as your own sibling. So in this case, we've got a no there. So what about symmetric? If X is a sibling of Y, is Y a sibling of X? Yeah, I'm going to say yes here. And I do like that comment, Eric, about the notion of leaves in the binary tree. Yeah, this idea of, what does it mean to be a sibling? Well, one way to phrase it is X is a sibling of Y if X and Y have the same parents. Well, I have the same parents as myself. So under that definition, I would be my own sibling. And that seems entirely reasonable when you say X is a sibling of Y if they have the same parents. But what we often read here as sibling is that X is a sibling of Y if X and Y are different people and they have the same parent. So that's how we're sort of interpreting this word sibling. But as in other cultures, it just may be the more succinct version that they share the same parents. And so you share the same parents as yourself, so you're your own sibling. But yeah, it's a kind of an interesting question. I won't say really anything more about that here, but it's something to consider just as sort of a thought process. Okay, how about transitive? If X is a sibling of Y and Y is a sibling of Z, is X a sibling of Z? Yeah, we're going to say yes here. Oops, I should have put this one in green. And I'm not talking in here about half brothers, half sisters, or half siblings, ones that share one parent but not another parent. But you could do that. I mean, you could go through this and talk about step siblings and the like as well. But I'm just going to focus our attention because we're just coming up with examples of equivalence relations that are sort of being used in everyday life. So we're going to trim these down just a bit and make them a little bit less complicated. Oh, I did want to show you this, so I'm just going to bring up a browser window. Because this is always fun. So I come from a fairly large family, lots of cousins, and all my cousins have children, and some of their children have children, etc. So one thing that's often, on my mind is if my cousin has a child and then they have a child, what am I to them? Is it my cousin? Is it my first cousin, my second cousin? What's this removal business? And one thing I find that to be very helpful is in Wolfram Alpha, if you just type in things like first cousin once removed, then it tells you what that actually means. So first cousin once removed. So the removal is how many generations apart you are. So the once removed means that the person I'm in reference to is one generation removed from me. So in this case, they're either up, or if this was me, they'd be down a generation. And the cousin part is the distance to the nearest ancestor. So a 0th cousin would be a sibling, right? A 0th cousin would be the distance is 1 to the nearest ancestor. So you'd be siblings. A first cousin, or a cousin, is a distance of 2 to the nearest ancestor. So if I say I'm a first cousin, it means we share the same grandparent, but we are once removed in that we have a generation gap between us. And so you can say, what happens if you got twice removed? Then because we are first cousins, we share a common grandparent. In this case, it's saying great-great-grandparents, but that's just because it's referring to this as a self. If I'm thinking of this as myself, then it's my grandparent, which is their great-great-grandparent. So we share, the common ancestors we share is one of us is within a distance of 2, but then the twice removed is there's a generation gap of 2 between us. So yeah, I love this. So here's the reason why I'm bringing this up, is if I write sibling, I think it comes up. Yeah, there we go. So if I write sibling, it distinctly shows 2 nodes. And so it's referring to self and other person. So this is built upon the fact that there is a person cannot be their own sibling. But again, if you're from a culture where the use of the word sibling means you can include yourself, then this would have to be changed based on your cultural background. So that's just a fun thing to see. Yeah, I really like that depiction, because that's the first time I actually understood cousins and removals, is when I saw the tree, and I was like, oh, that makes total sense. Now I can figure out what my relation is to all my cousins, first cousins, second cousins, and so on. All right, so back to the question at hand. So a sibling, it's not an equivalence relation because we don't have check marks across the board. It was reflexive was the problem. But if, for example, if you're Malaysian descent and you do refer to yourself as your own sibling, then it is an equivalence relation in Malaysia, for example. How about the child of? So X is a child of Y. Let's go through these fairly quickly. Are you your own child? No. Symmetric. If X is a child of Y, is Y a child of X? And the answer in there again would be no. How about transitive? If X is a child of Y and Y is a child of Z, is X a child of Z? Yeah, no, it wouldn't be child, but it'd be a grandchild. So there'd be a way to sort of modify this. So we got X's across the board. Of course, X is not an equivalence relation. How about this next one? Lives in the same city as. Now I'm just assuming that everyone has a singular city of residence where they reside at this moment in time. So you can't say, well, I have houses here and there, and so I live in both. No, we're just going to assume every person has a singular city of residence. Let's say it's the city they vote in, for example, or the constituency they vote in. So X related to Y if X lives in the same city as Y. Is it reflexive? Well, yeah, I live in the same city as myself. So that's a check mark, reflexive. If X lives in the same city as Y, does Y live in the same city as X? Yeah, it's symmetric. If X lives in the same city as Y and Y lives in the same city as Z, does X live in the same city as Z? Yeah, all three would live in the same city. So this would be an equivalence relation. And so there's an example of an equivalence relation on the set of all people. And it turns out that this is an equivalence relation. And maybe city isn't the correct term to use here, but constituency certainly is. This is an equivalence relation that we use all the time during election periods. People are always grouped into constituencies, which is where they're going to vote for their representative. And so we've got an equivalence relation that we use all the time in our electoral system. In fact, what our electoral system actually consists of is for everybody in this one constituency, we are selecting one person to represent us. And that one person is supposed to be a representative of this class of people that all live in the same constituency. So I'm starting to use words that we're going to see in the next definition. For an equivalence relation, we can define all of the people who are related to each other, or all of the elements in A that are related to each other. We can call that an equivalence class. And one representative of that class is called a representative of that class. And so here's our next definition. If tilde is an equivalence relation on a set A, for a particular element of A, we use square bracket notations around A to denote the set of all elements of A that are related to A. So all the X such that X is related to A under the equivalence relation. This is called the equivalence class containing A, and A is called the representative of that equivalence class. So the nice analogy is to think about this in terms of constituencies and sort of voting blocks, and that for a given person, they form a collection of all people that live in the same, let's call it the same city as them. Let's imagine the constituency is a city. And I form a representative of my city, for example, the city of Burnaby. But so does everybody else. Everybody else is a representative. And in fact, there is one representative that sort of takes the prestige above everyone, and that would be like the mayor or some formal political representative of the city. And they're sort of the representative or for that equivalence class. So that's sort of the idea with these equivalence classes. Now that leads us to the connection I want to make with partitions. And that is, if we have an equivalence relation on a set, then we get these following properties: that X, for any X, it's in its own equivalence class. So X is a member of its own equivalence class. If two elements are related to each other, then their equivalence classes are the same. So the equivalence class of X is the equivalence class of Y. And if X and Y have the same equivalence classes, oh, sorry, I shouldn't say it that way. X and Y, for any given X and Y, either their equivalence classes are the same or they are disjoint. And that's really where the partition aspect is coming into play. So let's actually prove this, that if we have an equivalence relation, then the equivalence classes behave in this way. So how are we going to do this? We're going to prove this part by part. So part A, I want to show that X is an element of its own equivalence class. Well, the first thing to note is that since tilde is an equivalence relation and it's reflexive, then X is related to X. But that's what it means to be a member of the equivalence class of X. I'll underline this part here. So since X, the thing on the left, is related to X on the right, then that means that X is an element of X. I'm just using this definition right here, that the equivalence class of A is all the X's that are equivalent to A. And so the equivalence class of X is all the things that are equivalent to X. But because it's reflexive, X is equivalent to X. So it's in its own equivalence class. So that's nice. It means that the equivalence class contains itself, or in other words, the representative of a class actually has to live in the class itself. So the representative of a city has to be a member of the city itself. So what about if X is related to Y? Then are the equivalence classes the same for X and Y? And vice versa. If the equivalence classes are the same, does that mean X is related to Y? Yes, and we will prove the two directions. So this direction first says, suppose X is related to Y. Now I want to show that the equivalence classes are the same. So what I'll do is I'll let Z be an element of the equivalence class of X. And I'm going to show that this also has to mean that Z is in the equivalence class of Y. So because it's in the equivalence class of X, Z is related to X. But X is related to Y. So by transitivity, Z is related to Y. And therefore, because Z is related to Y, Z is in the equivalence class of Y. And so that means I started with any element of the equivalence class of X, and it has to be an element of the equivalence class of Y. So it means that X, the equivalence class of X, is a subset of the equivalence class of Y. Similarly, we can do the reverse. Similarly, the equivalence class of Y is a subset of the equivalence class of X by the exact same argument. So the equivalence class of X is equal to the equivalence class of Y. So that means if two elements are related to each other, then their equivalence classes are the same. The next direction we need to prove is we need to suppose their equivalence classes are the same. Suppose X, the equivalence class, all things related to X, is that set is the same as the set of all things related to Y. What does that mean? Well, because by part A we know X is in the equivalence class of X, and that is in the equivalent, or that's equal to the equivalence class of Y, that means X is an element of the equivalence class of Y. And that means, therefore, since X is in the equivalence class of Y, it's related to Y. And so we get the opposite. If the equivalence classes are the same, then the elements are related. And the last one, we're going to show that equivalence classes are either equal or disjoint. And so what we'll do is we'll suppose they're not, well, maybe I'll write it this way. Suppose they are not disjoint. So the intersection is not empty. Then there exists some Z in their intersection. And so that means that Z is related to X and Z is related to Y. But that means that Z is related to X and let's say, actually I want to switch the first one. Sorry, which one do I want to switch? I want to switch the first one. Due to symmetry, X is related to Z and Z is related to Y. So that's by symmetry. And because X is related to Z and Z is related to Y, we have X is related to Y by transitivity. And that's what we wanted to show, because X is related to Y by part B, we know that their equivalence classes have to be the same. And so what that says is that if the intersection is not empty, then the sets are the same. So they are either, the two equivalence classes, they are either the same or they have nothing in common. They're completely disjoint. And so that's our main result about equivalence relations, is that when you have an equivalence relation defined on a set of objects, you can form equivalence classes. For any element, you just form the set of all things that are related to it. And those equivalence classes have these three properties: that every element is a member of its own equivalence class. And if two elements are the equivalent, then their equivalence classes are the same. And equivalence classes form a partition in some sense. That's really what, well, that's what A and C are really telling us, is that they are a partition. And so that gives rise to this next year, this idea of a partition now, that if A is a set and R is an equivalence relation, then the equivalence classes form a partition. And the second part is, if we have a partition on a set, then we can define a relation on it by saying two elements are related if they live in the same part of the partition, and that turns out to be an equivalence class, or sorry, an equivalence relation. So two elements are related if they live in the same partition. That's an equivalence relation, because it satisfies the property of being transitive, symmetric, and reflexive. So this theorem, theorem 17.3.2, really says that if you want to partition things into sets, one way to do that is to create an equivalence relation on the set and let the equivalence relation do the partition for you. And that's really what we're going to be using with the Rubik's Cube and the like, and in our other aspects of groups, is an ability to form a particular equivalence relation that partitions it into nice sets that allow us to do some analysis. So let's look at an example. Maybe before we get to the one example, we'll talk about, well, actually, before I get to the class of representatives, we'll talk about the example, and then we'll see what that definition says about the particular example we have in mind. So what we're going to do is we're going to define a relation, and I'll just use the triple equal sign, because that relation, it'll turn out to be an equivalence relation. So we'll use that, and it's one that we're used to seeing anyway. We're going to define this relation on the integers by X is related to B if the difference is divisible by 2. So we call this the congruence relation, modular congruence relation, mod 2. So A is related to B, mod 2, if their difference is divisible by 2. So this is something we've seen before. Is it reflexive? Yeah, because A minus A is 0, and that's divisible by 2 for any A. Is it symmetric? Well, A minus, maybe I'll write this down. Yes, it's symmetric because 2 divides A minus B implies 2 divides B minus A. In other words, if A minus B is even, then B minus A is even. Is it transitive? Well, let's figure out whether it is or not. Suppose A is equivalent to B mod 2, or congruent to B mod 2, and B is congruent to C mod 2. Then what does that mean? That means that 2 divides B minus A, and 2 divides C minus B. So it means that both of these are even. But it also means that their sum is even. So maybe I'll say it this way. B minus A and C minus B are even. So that's just a restatement of the line below. And that might make it easier to see that if that's the case, then B minus A plus C minus B, which is C minus A, is even. And because C minus A is even, that means A is congruent to C mod 2. And therefore it's transitive because we had A was congruent to B was congruent to C, and therefore A is congruent to C. So therefore it's transitive. So we got that check mark there too. And so what this means is that this relation on Z is an equivalence relation. So because it's an equivalence relation, it partitions the set of integers into equivalence classes. So let's go ahead and see what those equivalence classes are. So our equivalence classes are going to be, well, I can pick an element and form an equivalence class with it. So I'll pick a natural element, I'll pick 0, for example. 0 is one element of Z. I'll form its equivalence class. So what's the equivalence class of 0? Well, those are all things that when you take their difference with 0, it's divisible by 2. In other words, they are all the even numbers, even integers. So like -4, -2, 0, 2, 4, ... And there is our representative of the equivalence class. It's in its own equivalence class. So that was the result we had before. X is an element of its own equivalence class. So here 0 is in its own equivalence class. What's another equivalence class? Well, I just need to pick something that's not already listed here. These are all the even numbers, so I'll pick 1. That's an odd number. And write down its equivalence class. So this will be -3, -1, 1, 3, ... These are all the odd numbers, and it's a member of its own equivalence class. And what we have is that this is really it. These are the only two equivalence classes. They're either even or odd. And so what we found is that Z can be rewritten as the union of these two sets. That's the partition aspect that we get, that Z has been partitioned into two equivalence classes. Now, 0 and 1 in this case are what we're going to call the class equivalence class representatives. So that's up here, definition 17.3.1 says that if you have an equivalence relation, then you can partition your set A into equivalence classes, pick one representative out of each class. Here I'm going to pick 0 and 1. And those are what we call the set of class representatives. And we denote that set by the A with this slash, this forward slash, and then the equivalence relation. So the class reps are given by this notation Z mod, and in this case, the relation is the triple equal sign. And this is where we list the representatives. And they're just 0 and 1. We didn't have to use 0 and 1. We could have used any element from the first set and any element from the second set. It's like an election process. For all the elements in the first set, they can select their own representative. I chose 0 because that's the most natural one to pick, but any one of them would have worked, and any one from the second set would have worked. So another set of class representatives would have been 2 and -1, for example. But these are the most natural ones to use, 0 and 1. And in general, we can do this. Doesn't have to be for mod 2 arithmetic. It could be for any modulus n. In this case, we have our congruence relation that we introduced at the very beginning of the course very beginning of the course, congruence mod n. We're now just putting these ideas in terms of a new terminology, new language. So the equivalence class of A under this mod n relation is just going to be the set of all integers who are congruent to A mod n. So those are basically the things for which B, the difference of B and A, it's a subtraction there, looked pretty short, so I'm going to rewrite it. B minus A. So for which the difference is a multiple of n. And we can write this as, if we sort of carry on through, that what does B look like? Well, B minus A is a multiple of n, or in other words, B is A plus a multiple of n. So the nice thing I can do is I could say, well, the equivalence class of A is really just everything that looks like A plus some multiple of n. And that's my equivalence class, A plus any multiple of n. And so our equivalence class representatives in this case are the natural ones to take would be 0, all the remainders basically, all the remainders you can get for division by n, 0, 1, 2, all the way up to n minus 1. And so those are our class representatives. And so things like when we say, what is 152 mod 7, the answer you usually give is the remainder when you take 152 divided by 7, and you answer in terms of these representatives. Is it 0? Is it 1? Is it 2? All the way up to, is it 6? And you answer with the corresponding representative. And so that's how this ties in with our questions about modular arithmetic. We typically always answer those modular arithmetic questions in terms of the representative or the remainder, if you want to call it that. Okay, so that's the equivalence relations. Now I want to just touch on, in the final 5 minutes, the ones that, the equivalence relation that's going to be the most important for us in terms of groups. And this is an equivalence relation that we define on a group related to a particular subgroup. And this is going to give rise to a bunch of results that we have. You know, for example, the order of an element in a group. It always divides the size of the group itself. These are things that we observed before. We're going to be actually able to prove this now. So some counting relationships between orders of elements and sizes of groups, etc. So what is our equivalence relation we're going to define? We're going to do the following. We're going to assume we start with a subgroup H of some bigger group G. And we are going to define a relationship on elements of our big group G. We're going to say two elements are related, what we usually refer to as related mod H. So this, I usually read this as A is related to B mod H. So maybe I'll write this here. Read A related to B mod H. If their difference is in H. This is really, it's just it's a complete analog to what we just did for integers and addition and remainders. Only here, or subtraction, I should say, we did A minus B is divisible by n. Only here, I can't be certain that my group operation is addition. So we're just going to write it in its generic multiplication group operation. And so for that, we're going to say A is related to B mod H if A inverse times B is in H. So that's a way of saying their difference is in H. So what does this give rise to? Well, what this means is that A inverse times B is equal to some little h for H and H. Or in other words, B is equal to A times H for some h, little h and h. So what this means is we say two elements are related modulo h if one of them is a multiple of the other one by an element of h. That's really what this is saying here. So differences in h, or one of them is a multiple of the other one by h. Is this an equivalence relation? Well, let's figure it out. Is it reflexive? To answer the question of is it reflexive, we have to consider for A in G, what is this equal to? Because I need to check. A is related to itself precisely when the difference of A and A is in H. And so A inverse times A is the identity. Yeah, because H is a subgroup that is in H, that means that A is related to A mod H. And so that means that this is reflexive. So that is reflexive. Is it symmetric? Well, we'll let A and B be elements of G such that A is related to B mod H. What that means is that A inverse B is in H, but H is a subgroup. So we're going to exploit those properties. If an element is in H, so is its inverse. So A inverse B inverse is in H, since H is a subgroup and therefore closed under inverses. But that means that taking the inverse of this is B inverse A is in H. The inverse of a product is the product of the inverses in reverse order. And that means that B is related to A. And so that means that this is symmetric. Is it transitive? Well, let's let A be related to B and B be related to C. And let's see if A is related to C. This says that A inverse B is in H, and the other one says that B inverse C is in H. So we have those two elements are in H. H is a subgroup. It's closed under products. So that means A inverse B times B inverse C is in H, since H a subgroup. And that means then that A inverse C is in H. Or in other words, A is related to C. So therefore, this is transitive. So this is just an analogy of the modular arithmetic relation, but now we're doing it for a general group. And we got that it's a equivalence relation. And I'm just going to write down one last thing here. Since it's an equivalence relation, then we know we can form equivalence classes to partition. So what is the equivalence class of a particular element A? Well, the equivalence class is the set of all things that are related to A, so or A is related to. If A is related to B, then that means that A inverse B is in H. Or in other words, it's a set of all B such that A inverse B is equal to H for some little h in H. Or in other words, this means that it's the set of all things where B is equal to A times H. So I'll write it as B is equal to AH for some H in H. But there's another way to write that then. This is really just saying it's all the elements that are of the form A times something in H. So I'll write it like that. It's just A times anything there is in H and form that set. And so this is what the equivalence class is. And what we do is, and just to find it down here, we call this a left coset of H. And these are going to be the things that partition our big group G. So we can partition G into H, a subgroup, and then I think of these AHs as various translations of our subgroup H. So I've got my whole group G, and I've got like an H here, and then I've got various translations of it, AH, BH, CH, and I can partition G into a bunch of copies of these things. And we'll argue that these are all the same size. And therefore, since they're all the same size and they union to all of G, then G has to be a multiple of the size of H. And that gives rise to this Lagrange's theorem that the size of G is divisible by the size of the subgroup H. And so I'm going to stop the recording here and we'll pick it up next day. and then we'll prove Lagrange's theorem next day. And then we may even be able to start touching on the Rubik's Cube as well.